this module, we will learn about capacitors and AC voltage applied to the capacitors. A capacitor is a device that can store a charge. A simple capacitor consists of two conducting plates separated by an insulating material called a dielectric. Unlike an inductor, which resists any change in current, a capacitor resists any change in voltage, thus ensuring a supply of constant voltage. Let us understand what happens when a capacitor of capacitance C is connected to a DC voltage source of potential difference V. When the key is closed, the capacitor gradually builds up charge as current passes through it. If the charge on it at this instant is Q, then the potential difference across its plates in the steady state is V is equal to Q by C. As plate A of the capacitor is connected to a positive terminal, positive charges accumulate on plate A. The positive charges on plate A repel the additional positive charges that the source tries to deposit on the plate. Thus, the capacitor resists the further build-up of charge on its plates. When the capacitor is fully charged, that is, the plates cannot take any more charges, the capacitor fully resists the current and the current in the circuit falls to zero. The state of a capacitor is known as a steady state. Now let's look at how a capacitor behaves if an AC voltage is applied across it. Consider a capacitor of capacitance C connected to an AC voltage source as shown. The instantaneous AC voltage, V, applied to the capacitor is denoted as V is equal to Vm sin omega t, where Vm is the amplitude of the applied AC voltage. Let this be equation 1. Now assuming the circuit to be purely capacitive, which means it has only a capacitor in the circuit, the instantaneous voltage across the capacitor is equal to the voltage supplied by the AC source. We shall make use of Kirchhoff's loop rule. According to this rule, the sum of potential differences across various components in the circuit is zero. Thus, we have V minus Vm sin omega t is equal to 0, which again leads to equation 1. As instantaneous voltage across the capacitor, V is equal to Q by C, we can write equation 1 as Vm sin omega t is equal to Q by C, or Q is equal to C into Vm sin omega t. Let this be equation 2. We know that current I is the rate of flow of charge in the circuit. That is, I is equal to dq by dt. Let this be equation 3. Substituting equation 2 in equation 3, we get I is equal to d by dt of CVm sin omega t. As C and Vm are constants, and as d by dt of sin omega t is equal to omega cos omega t, we have I is equal to omega Vmc into cos omega t. Let this be equation 4. By trigonometric substitution of cos theta with sin theta plus pi by 2, we get equation 5 as shown. This equation can be represented as I is equal to Im sine of omega t plus pi by 2, where Im is equal to omega Vmc. Let this be equation 6. The amplitude of the current, Im, can also be expressed as amplitude of voltage, Vm, divided by 1 by omega c. Let this be equation 7. Here, 1 by omega c is analogous to resistance and is called capacitive reactance. Capacitive reactance is denoted by Xc. Hence, this term capacitive reactance is denoted by the inverse of the product of angular frequency, omega, and capacitance C. Let this be equation 8. From equations 7 and 8, we get the amplitude of the current, Im, as the amplitude of the voltage, Vm, divided by the capacitive reactance, Xc. On close inspection of equations 1 and 6, which are derived for the value of current in the circuit, we can see that the current leads voltage in phase by a factor of pi by 2 compared to voltage. The phasor diagrams for analyzing the relationship of lead or lag between current and voltage is as shown. This lead in phase by pi by 2 units is equivalent to a lead in time by 1/4 of time period t. Another thing to note is that the maximum value of the current in the circuit is achieved at exactly 1/4 the time period of every cycle before the maximum value of voltage is achieved. Let us now try to look at power dissipation through the capacitor compared to resistance. The instantaneous power supplied, P, to the capacitor is denoted by the product of voltage with current through any circuit element. Using equations 1 and 4 and the relation Im is equal to omega Vmc, we get P is equal to Vm sine omega t into Im cos omega t. Since sine omega t into cos omega t is equal to 1 by 2 sine 2 omega t, we get P is equal to Vm Im by 2 into sine 2 omega t. Let this be equation 9. This instantaneous power here evaluates as a time-dependent harmonic function. As the average value of sine 2 omega t over one cycle of AC is equal to 0, the average of power P over one complete time period will be 0. Hence, power supplied to a capacitor on average in a circuit is 0. This can be seen as displayed by plotting a graph representing power supplied over time. As shown in the graph, we will study the charging of the capacitor in the 4 time periods marked as 0-1, 1-2, 2-3, and 3-4 respectively. As in the first time interval, 0 to 1, the value of the current keeps decreasing in the circuit from being maximum at time t is equal to 0 and reaching 0 at 1 at 1/4 of its time period. By the end of this time segment, plate A gets fully charged with positive charges and plate B with negative charges, and they oppose any further current in the circuit. The plates are fully charged at the instance 1. The voltage across the plates is in phase with the charge Q, and peaks at time t is equal to 1. As the current and voltage are both positive, it means that the power is positive. Positive power refers to charging of the capacitor. Hence, power is being absorbed by the capacitor and it gets charged. In the second time interval, 1 to 2, the current changes direction. Thus, the accumulated charges on the plates reduce. The voltage reduces but remains positive. Since the voltage is positive and the current is negative, power is negative. Negative power refers to discharge of the capacitor. Hence, energy previously absorbed by the capacitor is now being returned to the circuit. In short, the capacitor is discharging in this part of the cycle. In the third time interval, 2 to 3, the value of current keeps increasing. Here, as the current now is in the opposite direction compared to the last interval, the charges on the two plates effectively interchange. Plate A is now negatively charged, while plate B holds positive charges. As the current and voltage are both negative, power is positive. Hence, energy is again being absorbed in the capacitor and it gets charged. In the last time interval, 3 to 4, the direction of current again reverses at 3. Thus, the charge begins to deplete from the capacitor plates, thereby reducing the effective voltage across the two plates. The voltage finally becomes 0 at 4. As the voltage is negative, while the current has become positive, it means that the power is negative. Hence, energy is again being released from the capacitor. Thus, finally at the end of the cycle, the capacitor returns to state 0 again. This cyclic discharging and charging of the capacitor, or more precisely, its conducting plates, in reverse polarities keeps taking place as long as AC current is established in the circuit. You have now reached the end of this module. In this module, you learned that a capacitor is an electronic component that can store an electrostatic charge. It can be similar to a tiny battery. A simple capacitor consists of two conducting plates separated by an insulating material called a dielectric. When the capacitor is fully charged, the charge on the capacitor opposes any further current flow through it, and the current in the circuit falls to 0 in a steady state. Capacitive reactance, Xc, is the inverse of the product of angular frequency, omega, and capacitance, C. Power supplied to a capacitor on average in a circuit is 0. The cyclic discharging and charging of the capacitor in reverse polarities continues as long as AC current is established in the circuit.